By the end of this diagram, you will be able to interpret a potential energy diagram. In previous lessons, we've learned about collision theory, which states that in order for a chemical reaction to occur, the reacting molecules must collide with the proper energy and orientation. And we're going to focus on the proper energy portion of that definition. We are going to look at how the energy changes throughout a reaction. What we have here is a general potential energy diagram, and I want you to focus on the axes first. So the y-axis is going to be a measure of the potential energy, and you can think of the origin down here as being 0, and it increases as you go up the y-axis. The x-axis is going to be either labeled as the reaction coordinate or reaction progress. And so what that means is as the reaction proceeds, this is going to be from start to finish. So start over here on the left with the reactants and then finishes over here on the right with the products. And there are a variety of lettered arrows that we're looking at, and we are going to define those. They are not always going to be the same letters. Sometimes they might have numbers associated with them. Sometimes the arrows won't be there. But just to give you a general idea of what a potential energy diagram represents, we're going to use these letters. So the first letter we're going to look at all the way over to the left here is letter A, and this is going to be the potential energy of the reactants. So going from 0 up to whatever value this would be here, that is going to be our energy of the reactants, where the reaction starts. Then if we look at arrow B right here, arrow B is going to represent the activation energy. And we heard this before when we talked about a catalyst. Okay, we'll discuss a catalyst again, but right now what we need to know is that an activation energy, in this case of the forward reaction, is the energy required for the reaction to occur. So from the reactants to the top of the energy hill. So forward reaction means we start with the reactants and we go forward. Reverse reaction would mean we'd start with the products and go backwards. But right now, letter B is representing the amount of energy it takes to start off with the reactants, to break those bonds, and to get up to the top here of that energy hill. Now, that energy hill is called the activated complex. And that activated complex is a very, very unstable state. It doesn't hang out for very long. It's when the bonds are broken in the reactants, yet the product bonds have not been formed yet. And in order for the reaction to get up and over this hill, just like a roller coaster, we are going to need to gain some amount of energy. That amount of energy is referred to as the activation energy. Arrow C is going to be the activation energy of the reverse reaction. So this is the energy required for the reaction to occur in reverse. So we're starting over here with our products and we have to get up to the top of the hill. So the difference between those 2 points in the graph is going to be referred to as the activation energy of the reverse reaction. Arrow D, this is an important one. Arrow D goes between the reactant energy and the product energy. So it's the overall energy change in the reaction. And we call that the heat of the reaction. So potential energy is usually measured in heat. And so from the beginning to the end, despite how we got there, despite our activation energy, the difference between those is called the heat of reaction. And this tells us a lot about a reaction. You can calculate this when there are numbers involved. You take the potential energy of the products minus the potential energy of the reactants. And so you can remember that as being pep-er. So you have potential energy of the products minus the potential energy of the reactants. And of course, this would be if you had numerical values, and that's how you'd calculate it. The important part is the sign of that value. So heat of reaction, the change in heat is represented as delta H. And if it is a positive delta H, that is an endothermic reaction because energy is absorbed. So, to end up with a positive value here, the energy of your products has to be greater than the energy of your reactants, meaning overall the reaction absorbed energy. If the delta H is a negative value, if its sign is negative, that means it is an exothermic reaction. Energy has been released. And the only way you can get a negative value from this math is if your potential energy of the products is less than the reactants. So if this value here is smaller than this value, you're going to end up with a negative value because overall energy has been released. And so if we look at the potential that we have, we can see that the products have less energy than the reactants. So this is an example of an exothermic potential energy diagram. So when the products have less energy than the reactants, we are going to call that an exothermic diagram. And if we were to just do a rough sketch of an endothermic diagram, it would look something like this, where the energy of the products is greater than the energy of the reactants, meaning that overall energy is absorbed. And then lastly, arrow E, that represents the potential energy of the products because it goes from 0, the bottom line, up to the product energy. And so that is just going to represent the ending energy. So not only is it important to be able to recognize these in a potential energy diagram, but you should also be able to determine the numerical value of all important parts of a potential energy diagram. So what we have here is another potential energy diagram, and you can tell that it is exothermic because the energy of the products is less than the energy of the reactants, meaning that overall energy is released. And we are going to identify the points to the right. So the first one is asking for the energy of the reactants. And so we start with the reactants. So that's the leftmost energy here, which is going to be 55 kilojoules. It's also asking us for the energy of the products. So we end with the products. So that's down here. And that's going to be about 30 kilojoules. So we're just estimating with what we have. The activation energy of the forward reaction. Forward reaction means we start with the reactants and we go forward to the products. And remember, activation energy is the energy required to start the reaction. So from the reactants up to the top of this energy hill. Think of it like a roller coaster. If you can't get up and over that roller coaster, the roller coaster ride is not really going to happen. The car is just going to come back down and you're going to end up where you started. So if we start at 55, and in order for the reaction to occur, we have to get up to about 80, the difference between those from 55 to 80 is 25 kilojoules. So it requires 25 kilojoules of heat for this reaction to occur in the forward direction. To go in the reverse reaction or the reverse direction, we start with our products right around 30 and we still have to go up to 80. So going in the reverse direction, the activation energy is actually much higher. So that's going to be 50 kilojoules, the difference between the products and the top of our hill here. And then finally, the heat of reaction. The heat of reaction always includes a sign to indicate whether it's endo or exothermic. And remember, we are going to do potential energy of the products minus potential energy of the reactants. So the potential energy of the products is 30. The potential energy of the reactants is 55, which gives us a value of negative 25 kilojoules. And so in order to be correct here, you need to include that sign. So our final answer is going to be negative 25 kilojoules. And so you should be able to identify a potential energy diagram as endo or exothermic, but you should also be able to write a reaction to indicate whether a reaction is endo or exothermic. So here we have a potential energy diagram of an endothermic reaction, and we can tell it's endothermic because the products have more energy than the reactants. A little review here: endothermic means that energy has been absorbed, so the products have a greater energy than the reactants. And here's an example of a reaction that's endothermic. This actually comes from table I in your reference table. Okay, their table I is listing a bunch of different reactions, and then it gives the delta H values for those. And notice how the energy value, 66.4 kilojoules, is a reactant. That means that energy has been absorbed. So if you see a reaction written with the energy value included, that means the energy has been absorbed if it is a reactant. And if energy is absorbed from the surroundings, then the surroundings would feel cooler. An exothermic reaction, where the products have less energy than the reactants, means there's been a release of energy overall. And notice that our energy value is a product here. Our energy value is a product because it's being released. And if it's being released into the surroundings would feel warm. So if we take a look here, I've given you 4 different reactions, and I want you to first identify the type of reaction as endo or exo, and then identify the delta H. So for example, this first one, I see the energy value as a reactant, therefore it is endothermic, and the delta H is given to me in the reaction itself, and because it's endothermic, I'm going to call it positive 66.4 kilojoules. So what I'd like you to do is pause the video and try the next 3 problems and then come back and check your answer. Okay, hopefully you didn't have too much trouble with those. The second example here is an exothermic reaction because heat is a product, it's being released, and its delta H would be negative 84.0 kilojoules. And a lot of times people get confused here because they see the negative and then they say, well, it's plus 84 in the reaction. But remember, in a reaction, the plus sign means in addition to or and. And so we have to remember that if it's exothermic, we have to give the delta H a negative sign. The third example here, our energy is a reactant, so this is endothermic. And as far as a delta H goes, we're going to call it positive 53 kilojoules. And then lastly, our fourth example is exothermic because our energy is a product and therefore the delta H will be negative. And so we're going to call that negative 483.6. All right, lastly, a potential energy diagram can also be shown when a catalyst is used. So if you think back to our previous lessons, a catalyst was something that sped up a chemical reaction. It made it happen faster. And the reason that changes the rate of a reaction is because it lowers the activation energy. So a catalyst lowers the activation energy. And what you can see here in this potential energy diagram is a dotted line that represents the catalyzed reaction and a solid line that represents the uncatalyzed reaction. And you can see that the dotted line goes underneath the solid line. So our dotted line represents a lower activation energy, and our solid line is our normal reaction. So when you have a lower activation energy, the reaction will happen faster. But notice what it doesn't change. It doesn't change where the reaction starts. It doesn't change where the reaction ends. So it lowers the activation energy, but it does not change the heat of reaction. And the heat of reaction is the delta H determined by product energy minus reactant energy. So if neither of those change, either does the heat of reaction. So the only thing a catalyst will change is the activation energy. And so, hopefully, by the end of this lesson, you are able to interpret a potential energy diagram, identify one as endothermic or exothermic, and be able to pick out or identify numerically the energy of the reactants, the energy of the products, the activation energy of both the forward and the reverse reaction, and the overall delta H or heat of reaction for a chemical reaction.